Welcome to Physics with Mr. Brazil. Today we're going to be studying centripetal acceleration in the vertical direction. This is a part 2 of a part 3 series. Part 1 and part 2 will be linked below so you can check those out. To start with, we're looking at, let's say, a ball being spun in the vertical by some tethered rope. So it has a tension. Well, if we look at the top portion of this, the tension is downward. The force of gravity is downward. And that means this whole system will have a centripetal force that is negative. So if you remember from the last video, centripetal acceleration is always towards the center because velocity is changing direction, and the equation is velocity squared over the radius, or 4 pi squared times r over t, which is time squared. And in this case, I put a ball that's 10 kilograms spinning at 8.5 meters per second with a radius of 4 meters. If we do our net force, and I'm going to call it y and top, then our tension is negative, our force of gravity is negative, and our centripetal force is also negative. Well, the negatives cancel. Actually, you can factor it out and they'll cancel out. So in other words, these all become positive. So tension will equal centripetal force minus the force of gravity because it was positive above it if you look at the equation. But we move it over, and if we just do our variables, velocity squared over r for centripetal acceleration minus g, our gravitational acceleration of 9.8 meters per second. Well, we'll plug those in and see what these values mean. And again, 8.50 meters per second squared. Do not forget to square it. Over 4 meters, 9.8 again, as I mentioned, meters per second squared. And this is going to give us 82.6 newtons for the tension on that cord. Well, how about, and I'm going to do this in a different color. Let's say now the ball's at the bottom here of this arc or this circle being spun. Well, in this case, the tension is upward, gravity is downward, and this whole system is accelerating or towards the center. Therefore, the centripetal acceleration is positive and towards the center. So I'm going to write this equation. This time it's going to be FY-BOT for bottom. So our tension, I don't know what happened there. That was strange. Okay. Our tension minus the force of gravity equals centripetal force. T will equal mass times velocity squared over r. I'm going to move the weight to the other side, and therefore it's going to be plus gravity. This is interesting. At the top, it's minus gravity. Now we're adding gravity. Well, this is going to make sense because it takes a little more tension because you're going to pull upward, okay, on that cord to hold that position where the ball's at. So if we put in 10 kilograms, 8.50 meters per second. Oops, not squared. Square the outside. Yeah, see, don't make those mistakes. Pay attention. Go slow if need be. And plus 9.80 meters per second squared. And this is going to give us a value of 279 newtons, which is considerable. Now, let's think about this. What if the tension is to the side here? In other words, horizontal. Well, that isn't going to change much because the force of gravity is downward and it doesn't, well, it plays, but it's in the y direction. Actually, we set up this, I'm just going to call it Fx in this case. So tension is going to equal the force of the centripetal acceleration. So in other words, T equals mv squared r. And if we plug this in, we're going to have 10 kilograms and 8.50 meters per second squared over the 4 meters. And that's going to give us 181 newtons. 181 newtons. So you can see there's a progression at the top. There's not much force. Towards the bottom, the force increases. And if you look at the middle, or I could have just cycled this, 82, 181, and 279. So the force should increase. And then as the ball passes the arc and spins upward, the force on, or the tension on the cord should decrease. Well, doesn't seem too complicated, right? Well, let's take a look at a different situation. How about we have, let's say, an object on top of a bridge, which is kind of like a circle, right? So we have a bridge, okay? In this case, we have the force normal actually downward and the force of gravity downward. We need to remember there are no centrifugal forces on the outside. Now, if we're looking at static friction, we'd have a normal force probably going upward here. But in this case, I'm looking at this system and a car going over a bridge, well, it's no different. What happens is the centripetal force is still downward, so it's negative. So when we set up this Fy, and I'll just say top again, and the normal force minus Fg minus MAC. Well, it becomes no different than before. So Fn will just be equal to, because all of these will become positive if you look upward. Now you'll see that it'll be equal to the centripetal acceleration minus gravity times its mass. And for example, we should also consider friction. The force of friction is horizontal, so there is no vertical, so there is no friction in the y direction. It's zero in that case. And I mean, we could do the hypothetical thing below, where if the car is going fast enough, and which is going to really need to go fast enough, because that normal force is going to go upward, Fg. But again, in this case, the force of friction is in the x direction. So even this equation will come out just like the ball on a tether. Don't forget mass squared r, but it's going to be plus g. Now, here's something that's a little more realistic. And you probably have seen clowns that have been inside a sphere, a spherical cage, and then they're riding a motorcycle, driving around, and going upside down in circles. There's a certain velocity that they got to attain and that type of thing. Well, that is no different. The math becomes no different. Again, I am going to put this in red. There are no centrifugal forces on the outside. So in this case, it is the same math. What's going to happen is on top, you're going to have Fn, Fg, and again, all the forces, just like in all the other situation. This one is going downward, minus, and on the bottom, Fn's up, Fg is on the bottom, and all the forces, the centripetal forces, are going upward. So that math does not change. So in this case, Fn mv squared r, this is just repetition, okay, just for you to note. But how about friction? There has to be, well, better yet, friction is in the x direction, doesn't show up. But there has to be a minimal force, let's say at the top. We're not so much worried at the bottom, but at the top, to keep an object going. What is that minimum velocity? So the minimum velocity for the top, how do you determine that? Well, in this case, we're really trying to overcome gravity. So in this case, top, for that minimum velocity, it's going to have to be equal to Fg. So and the centripetal force has to be equal at least to Fg to make it. So in other words, you want to go faster than this minimum velocity. So if we write this all out, mg equals mv squared over r, m cancels. So the mass is not important. It's no different than a falling object. But the velocity does become the square root of g times r. That will give you your minimum velocity. So if you're trying to determine that, you're going to have to do this type of math. Okay, check out part 3. Part 3 is going to be a little different. That one will be looking at objects at an angle. So either above the circle, below the circle, and how to determine those, plus the friction that's required, especially for internal circles and exterior circles. Okay, keep practicing physics and enjoy. Bye.